Well, hello everyone. It is 9 a.m. for our first synchronous online session. My plan here was to go ahead and record lectures for the material I wanted to cover, and I'll go ahead and just do that. If you happen to chime in while we're talking, great. If not, you'll be seeing this later, and I'm more than happy to answer your questions afterwards. The two topics we want to talk about today are finding things in the night sky and the cause of the seasons. And I have a couple of activities for you to do on these topics. If you go to our syllabus, which is located on Canvas, you'll see that there's two activities. The Finding Things in the Night Sky activity, this is listed for Thursday, and the activity Cause of the Seasons. I'm going to introduce those today just so you can see what the idea we have behind those things. You can find those activities in your activity book. One of them, the first one, is designed for use with a planetarium, so I'm going to have you download a planetarium software that you can use on your computer to complete that, and it also assumes that you have some help, so a friend or a family member or somebody like that who can play along with you. It should be kind of fun. Okay, so let's go ahead and get started. The notes for what I'm going to be talking about today on our Canvas site. You can find those in the Files site, and I will also link those to the topics. There are notes you can get to just see what I'm going through here. Okay, so let's take a look at our first topic, which is finding things in the night sky. It's important to be able to know where you're looking to find things in the night sky. If I tell you where a particular object is, we need some way to describe that to each other. We need some system for determining where things are in the sky. And this is something that you can use whether you happen to be going outside and doing some stargazing just by yourself or with some binoculars or a telescope, or if you happen to be working with folks in other parts of the world where you want to look at the same stuff at the same time. So what are some methods for looking at things in the night sky? Well, if I want to tell where something is, the easiest method is, of course, to just point at it and shout. Say, hey, look out, there it is. This works out very well for things like meteorites or impending cometary impacts. Not terribly great for faint objects, but it works out great if you're looking for bright things. The second way that we look for things in the night sky is by using regions of the sky called constellations. Now, these originally were starry patterns in the sky that people would attribute to different stories in their mythology, but now astronomers use those as just to describe regions on the sky. I think of them sort of like states. If you imagine asking somebody to go look at the state of Utah on a map, it would be like going to look at the constellation Orion on a map of the sky. They're more precise, but it requires a common framework. We all have to decide what Orion is. And they are, again, they're more precise than point and shout, but they're still just pointing at a region of space. The next one that I'll show you in just a moment on the planetarium is altitude and azimuth. Now, this is incredibly precise, but it's only good locally. That is, it only is good for looking at things from your location on the planet Earth. And then the next one we're going to talk about is right ascension and declination, which I'll demonstrate in just a second, and that's precise and good for any observer. We're going to talk about altitude and azimuth first. So we'll measure altitude in degrees, and we measure azimuth in degrees, and so let's see what that looks like. So I'm going to bring our planetarium program up and make this as big as we can so you can see this. I'm kind of trying to keep an eye on the video here so I see what you're seeing. Okay, so we're looking north, and as I mentioned, I was trying to mention before, that we have, if you're looking north, you can usually find the Big Dipper. Now, what you're going to see from Ogden is more like this, right? Because we have a lot of light pollution. If I turn off the atmosphere, which I can do in the planetarium, it's going to look like this, right? So there's a lot of stars you can't see from Ogden, but if I turn this on, you can see some stars. So this is, or you can see a few stars, and it's easy to pick out the Big Dipper because it is the largest constellation in the north that's very bright. One of the stars you want to keep an eye on in the sky is the North Star, because that always tells you what direction you're pointing. And this is the Big Dipper. Big Dipper, if I follow the arc of the Big Dipper down to the cup, these two stars at the end of the cup point directly up to the North Star. And if I click on that in Stellarium, it shows me all of this information about the North Star. Probably more information than you want to know at this point, but by the end of this course you will understand what all of this stuff means. For right now, it's really just a dot in the sky. So that's Polaris, that's the North Star, and the North Star is directly over the northern part, or directly over north in our cardinal directions. So there's you can always find north if you just find the North Star. The altitude of our North Star is always your latitude. So depending on where you are, you can tell if you're near the equator, this thing is going to be close to the horizon, and if you're near the pole, it's going to be further overhead. So that introduces our first coordinate system, which is altitude and azimuth. Now, if you're playing along at home with Stellarium, there's let me just give you a brief tour of how this program works. There are some toolbars down in the left-hand side and in the upper right. Okay, there's the North Star again. You probably won't need this stuff up here. This is for stuff if you happen to be using a telescope. But the stuff down here you'll be interested in. You can do things like click on the constellation lines, so you can see if you're having a hard time finding the Big Dipper, you can find the Big Dipper here, which is part of Ursa Major. And you can turn on the constellation names if you want to see where the constellations are. So you can do this at home and then go outside and look at these constellations in the sky. So it's kind of a fun thing to be able to do with this program. You can also turn on the constellation diagrams. Wow, this is really cool because it's showing the pictures of Draco and Ursa Major, Ursa Minor and Ursa Major, which are bears, and then you've got the giraffe and all sorts of things. So again, this is what I was saying about the common framework, right? If you know all these stories, then you know what these constellations are. But you can turn those guys on and off as you want. Other things down here, you can turn the ground on and off if you want to see what's below the ground. You can turn the cardinal points on and off. You can turn the atmosphere on and off. I'm going to turn the atmosphere off. And then you can also display deep sky objects like galaxies. You can turn the planets on and off and things like that. There's some tools here for modifying the field of view. The one I like is being able to go full screen or not full screen. So if I click on that, I can go to full screen. If I click on it again, I can go to partial screen. Okay, so that's pretty much the basics for how Stellarium works, and you navigate around by moving your mouse, clicking and moving your mouse. If you use your scroll bar, you can scroll in and out like that. So take a moment to sort of play around with this when you get a chance. So now that I've found Polaris, I want to talk about our altitude and azimuth coordinate system because it's based on north. It's based on our cardinal directions. And I can turn that on down here by just clicking on the azimuthal grid, right? So that's what we call our altitude azimuth coordinate system. So I click on that, and you'll see a grid lines showing up on our sky. And our grid lines are lined up with north, right? You see they're perpendicular to the ground at north, perpendicular to the ground everywhere. And if I go around, you see that there is a nice square grid that's based on our horizon all the way around south. And if I keep going around to west and around to north. So the azimuth, which is the direction around the cardinal points, is telling you what direction you're looking. So if I say an azimuth of 0 degrees, that's north. If I say an azimuth of 180 degrees, that's south. So that's the azimuth. The altitude is how far off the horizon you are. So the Polaris, if I look up from north, I know that its azimuth is 0. If I look up from north, I can see that Polaris is located right here. And I can go over here and read off, and you probably won't be able to see this on my screen, but you can read off here, and it's about at, let's see here. Let's see. Here, it's at about 42 degrees, because if I follow this one around, that says 40 degrees, and this is a little bit further up. So we're at about 42 degrees, which is about the latitude of Ogden, Utah. So that's kind of handy that the Polaris is always telling you your latitude. And there's one other point in altitude and azimuth that's important, and that is the one directly overhead. So if I look directly overhead, I see that all of these lines converge on a single point, and that point is called the zenith. And that point is directly overhead. If you go outside and point straight up, you see the zenith. Okay. So that's altitude and azimuth. It's based on the cardinal points, north, south, east, west, and it's based on the altitude above the horizon. And they're both measured in degrees. And here's a handy little tip. If you go outside tonight to look at this, your fist extended at arm's length, I don't know if you can see the video here, your fist extended at arm's length is 10 degrees. So if you want to practice measuring altitude and azimuth, you can go outside and hold your fists at arm's length, and then use those to measure 10 degrees off the horizon. And if you go out and find the North Star tonight, find the Big Dipper and find the North Star, you should be able to see that the North Star is about 4 fists, a little bit more than 4 fists off the northern horizon. And that just tells us our latitude. And that's handy because if you ever get kidnapped and get dumped off at, Barrow, Alaska, you'll be able to tell what your latitude is. Okay, so questions about that before we move on, altitude and azimuth, since we have a few people on deck here. Okay, so no questions there. Let's move on. I want to talk about right ascension and declination, because the limitation to altitude and azimuth is that it doesn't do much if we are located someplace else. Take Polaris for example. If I look at Polaris, its altitude and azimuth is 0 degrees azimuth and 42 degrees altitude, but if I move to a different location on the Earth, its azimuth doesn't change, but its altitude does. And so if I asked you to go out and look at Polaris, and you happen to be located in Florida, but I gave you the altitude and azimuth from Ogden, you wouldn't be able to see it. You'd have to look at a different altitude. So we need a different coordinate system, and that coordinate system is called right ascension and declination. And right ascension and declination is also known as equatorial coordinates. The right ascension is measured relative to the meridian, which I'll show you in just a second, and the declination is measured relative to the celestial equator. So let's turn off our azimuthal grid and turn on our equatorial grid, and you will see that the equatorial grid is not perpendicular to the horizon, and the 0 of the equatorial grid is this line that kind of comes down right here that intersects with west, and if I go over to the other side, the 0 line also intersects with east. So you can see that right there. Okay, so we have a coordinate system that's based on the celestial equator. This is the 0 degrees, and then if you probably can figure out where the pole of this coordinate system is, it is at Polaris, or pretty close to Polaris. Polaris is not quite at the North Pole of the celestial sphere, but there it is. So that's where all the lines converge, which is on the northern celestial pole, and the 0 point is at the equator. So you can think of this like a giant sphere that extends out from the Earth, that's centered on the equator and the poles of the Earth. So we can see that there's a north celestial pole, and we can't see the south celestial pole from here, but there is a south celestial pole that is located beneath the southern horizon. Now the handy thing about right ascension and declination is that it is the same for all observers. So the right ascension is like longitude. It's measured with these lines right here that radiate out from Polaris, right? And those are labeled in hours. So let's see if we can find those. I'm going to have to turn off my ground here so I can see them. So if I turn off my ground, yeah, here we go. You'll see we have the hours of right ascension. This is 14 hours, this is 13 hours, this is 12 hours, 11, 10, 9, all the way around the clock. And you might think about why we use hours instead of degrees for right ascension, and that's because the celestial sphere rotates, right? Or I should say the Earth rotates under the celestial sphere. And so it's just a handy way of measuring around the sphere because it's in time. And so you know that if you have an object that's directly overhead, you know that 1 hour later it's going to be 1 hour of right ascension off to the west. Okay, so that's right ascension. Declination are these things that are equivalent to latitude. So 90 degrees declination is the pole, 0 degrees declination is the equator. Let's see if we can find that. 0 degrees declination is the equator, which is right here. You can see this little number up here, 0 degrees down, and 0 degrees equator always intersects with west and east. Okay, so the handy thing about right ascension and declination is that it can be used regardless of where you are. Now the activity that I have for you, what you're going to do is you're going to sit down with a friend using this program, and you're going to pick some region of the sky, and hopefully you won't they won't know what you're looking at, and you're going to draw a little constellation or something like that, and you're going to label it with the altitude and azimuth and the right ascension and declination, and then try to see if you can have your friend find what you were looking at. Now it's fun to try to do it without using these guides, although feel free to use the guides because I'm sure you know as you get practice with this you might need them. But when you're looking for things in the night sky, you can tell people what the right ascension, declination, and altitude and azimuth are, and they should be able to find them. And then you can do fun things like change the location. Like if I went to Florida instead, and you'll see that the object you're looking at isn't where you think it is, and you have to go find it again using either the altitude and azimuth or right ascension and declination. Now if I choose a particular object, I'm going to choose Polaris again. There's a whole bunch of information up here that you can start to figure out, right? So we're going to talk about magnitudes later. Don't worry about that too much, but right ascension and declination, you now learned about these. You know that the right ascension is the equivalent to the longitude on the celestial sphere, and you know that the declination is equivalent to the latitude. So the fact that this is 90 degrees practically tells us that we're very close to the pole. It also tells you altitude and azimuth, right? Now that's going to depend on location, so let's do something fun here. Let's take a look at altitude and azimuth. You can see that we're at 0 roughly azimuth because we're in the north, and we're at about 42 degrees altitude. So if I go to a different location, say Texas, and look at my altitude and azimuth, you'll see that the azimuth is about the same, but the altitude has changed, right? And the altitude has changed because we're further south, and so therefore the northern pole is directly closer to the horizon. Okay, let's go back to Ogden. I'm not probably warmer in Texas, but let's go back to Ogden. Okay, so that's altitude and azimuth. Questions about that before we continue? Okay. The last thing I want to point out on this program before we move on to the seasons is something called the ecliptic. Now this program doesn't allow me to show you the ecliptic directly, but I can do it, and you can find the ecliptic by looking for the planets. So we're going to make sure our planets are turned on, and we're going to try to find some planets. Oh, there's some planets. There's Jupiter, and let's see if we can find some more planets. Might zoom out a little bit. Let's see if we can find some planets. Actually, why don't I do this? Let's bring the sun back up, because the sun makes a good reference point. Just wait for the sun to come back up. Oh, we're looking to the east. We'll look to the west. Here we go. All right, so there's the sun. Okay, so we see the sun here on the horizon, and then we see the planet Venus, and we see the moon, and if I keep going up like that, I should see Jupiter. Okay, so Jupiter and the moon and the sun all fall on something known as the ecliptic. And the ecliptic, as you might think from the name, is where the eclipses occur, and that's basically the plane of our solar system. So the plane of our solar system occurs where you see all the things lining up in the sky. So if you go outside tonight near sunset, you should be able to see Venus just barely. You should be able to see the moon, and if you wait a little bit, you should be able to see Jupiter right after sunset. And those all form a little arc in the sky, which makes up what's called the ecliptic. Now that ecliptic is not the same as the equator, and you can see that because the ecliptic is tilted relative to the equator. This is the ecliptic here, and the equator is going to go like this. And so that means that the Earth is tilted relative to the plane of the solar system. And it's that tilt that is going to be important when we start talking about the seasons. Okay, so just some data on the ecliptic right here. The plane of the solar system, that's the thing called the ecliptic. The Earth is tilted by about 23.5 degrees relative to the ecliptic, and that means the equatorial coordinates are also tilted by 23.5 degrees. And if the Earth was not tilted, the ecliptic and the equator would be the same, but because the Earth is tilted, they are different. And that's going to be something we bring up here in just a moment. Okay, so to review, there was a bunch of vocabulary in this that you probably want to go through your book and remind yourself what these things mean. I've just listed them here in the notes so you can keep a track on what those things are. Those altitude and azimuth are associated with the zenith. The celestial equator and celestial pole are associated with the meridian. Oh, by the way, I guess I didn't mention the meridian. The meridian is the line across that goes through north and south. So the meridian would be, if I look directly south, this is a meridian. The meridian goes from south all the way through north. Okay, well, got lost here. South through the north. Here it comes down like this, south to north. Okay, and the ecliptic is the plane of the solar system. So just some quick questions, something you might want to think about. What is the best method for finding things in the night sky? This is an interesting question you might think about based on all of these things. I'm not going to answer it right now. Just want you to keep an idea of what the best method is. And I'll give you a little hint. It probably depends on who you're trying to talk to. So if you find the best method for finding things in the night sky, or the best method for professional astronomers to find things in the night sky, and these are things you'll be answering in your activity